is Babatunde, and we'll be continuing our lectures from where we stopped the other time. We started with single phase series AC circuit, and we were able to go through purely resistive AC circuit. We did something on purely inductive AC circuit, and we did something on purely capacitive AC circuit. We were able to show that in purely resistive AC circuit, we have the current and the voltage in phase, but in the purely inductive AC circuit, we said the current lags the voltage by an angle of 90 degrees, and we also talked about the purely capacitive AC circuit, that the current leads the voltage by an angle of 90 degrees, and we did some calculations, and we proceeded to RL series AC circuit. So I expect you to go back and do your revisions on them, and we also did something on the RLC series AC circuit. So I think that's how far we have gone. So in this lecture we'll be dealing with RLC series AC circuit. So our learning objective is that by the end of this session you should be able to calculate the impedance, the phase angle, the resonance frequency, the power factor, the voltage, and the current in a RLC series circuit. Also, you should be able to draw the circuit diagram for an RLC series circuit. You should also be able to explain the significance of the resonance frequency. So AC series circuit, when alone in the circuit, inductors, capacitors, and resistors, they all impede current, that is, they resist current. We have discussed that before. So how do they behave when we combine the three of them together? That's what we are going to learn in this lecture. Interestingly, the individual resistance in ohms do not simply add up, as we have seen the other time. Why do they add up? Because they are phasors. They are in phasors, because the angle between them is there's an angle between them, so they do not just add up, they are phasors. So we take the phasor sum. So because inductors and capacitors behave in opposite ways, they partially or totally cancel each other's effect when they are both in the circuit. So this diagram shows an RLC series circuit with an AC voltage source. As you can see, as I told you the last time, in a series circuit the same current flow through the elements, whereas the same current flow through the elements, whereas across the elements the voltage drop are different, and they depend on the magnitude of these elements. So I said figure 1 shows an RLC series circuit with an AC voltage source, the behavior of which is subject of this discourse. So the core of the analysis of an RLC circuit is the frequency dependence of X and XC, and the dependence of the XL and XC is what we use to usually do circuits that we use for transmission in radio industry. So this gives rise to the frequency dependence of the circuit with important resonance features that are the basis of many applications such as radio tuners. So the combined effect of resistance R, inductive reactance XL, and capacitive reactance XC is defined to be impedance. When we say to impede, to resist, so that's where we get impedance from. So an AC analog of resistance in DC circuit. When we are talking about DC circuit, we call it resistance. But when we get to AC circuits, we call them impedance. So in an AC series circuit containing resistance R, inductance L, and capacitance C, the applied voltage V is the phasor sum of VR, VL, VC, and VC are antiphase. VL and VC are antiphase, that is, they are displaced by 180 degrees, and there are 3 phasors diagram possible, each depending on the relative values of VL and VC. So if you have an RLC circuit, if you want to draw the phasor, it can exist in 3 forms. That's what we are trying to say here. And this is the first one, that is when XL is greater than XC. When XL is greater than XC, this is the circuit diagram we are going to have. So this will be XL minus VC, this is VC, this is VR, and this is V, which is the phasor sum of the VC and VL. So this is the impedance diagram. It is similar to what we have drawn before in the other classes. And when we want to obtain the Z, now if you look at it, it's similar to one of the things we have done. The Z will be R squared, which is this R squared, plus XL minus XC squared. And what is XL minus XC squared? Is this Z. This Z is equal to XL minus XC. So XL minus XC squared. And to find the angle, to obtain the angle, we can find the tan. We say tan phi of this angle is equal to what? XL minus XC divided by R. So this is the second option. When the first option, this is the first option, and the second option is when XC is greater than XL. The second option is when XC is greater than XL. And what happens is just like the other one, but the magnitude of VC minus VL is in the negative direction. So we know that our VC is what? IXC, and our VR is what? IR. So, and we know that our VL is what? IXL. So if you look at it, the one that is greater is the one that is at the front, VC minus VL. Yeah. So similarly, like what we did the other time, we say when XC is greater than XL. So our Z will now be equal to R squared plus into bracket XC minus XL squared. So if you look at it, this is XC is coming first because it has the higher magnitude, and we deduct XL from it and we square it. So the tan alpha is what? XC minus XL over R. And we can have a case where XL is equal to XC. That is series resonance. That is what we call series resonance. Series resonance occurs when XL is equal to XC. And if you look at this, this is the diagram. This is a VL of same magnitude as VC of the same magnitude, and this is the VR, and this I is in phase with this VR. So we are going to look at an example so that we know we'll be able to understand what you have been saying. So the example says that a coil of resistance 5 and inductance 120 millihenry in series with a 100 microfarad capacitor is connected to a 300 volt 50 hertz supply. Calculate A, the current flowing; B, the phase difference between the supply voltage and the current; C, the voltage across the coil; and D, the voltage across the capacitor. So as we always do, we list what we have, and from there we proceed to what we don't have. So if you look at it, we are given the resistance, which is 5 ohms. We are given the inductance, which is 120 microhenry. We are millihenry, sorry. We are given the capacitance, which is 100 microfarad. We are given the voltage V, which is 300 volts. We are given the frequency F, which is 50 hertz. So what we don't have the current flowing in the circuit. What we don't have the phase difference between the voltage supply and the current, and we don't have the voltage across the coil. We also do not have the voltage across the capacitor. So how do we solve this? We can draw the circuit diagram. If you look at the question, it said a coil of resistance 5 ohms and inductance 120 millihenry. These are the two. They are in series. The question says they are in series. So you draw your resistance and draw your inductance in series. So these two that are in series is the coil. This is the coil. So it is in series with a capacitor. This is the capacitor, 100 microfarad. So this is the coil and this is the capacitor. And what do we have? It is connected to a 300 volt source and 50 hertz frequency. So you should be able to produce the circuit diagram. So the first thing is to find our XL, and we know from previous class that XL is equal to 2 pi FL. And what is our F? Is our frequency 50. Our L is what? Is our inductance, and it is what? 120 microfarad. That is 120 times 10 raised to the minus 3. So if you do the multiplication, you should get 37.70 ohms. So we are also going to find XC. So what is XC? Our XC is 1 over 2 pi FC. So if you slot in the values, because our C is what? Our C is 100 microfarad. Microfarad, when you say micro, is 10 raised to the minus 6. So if you press your calculator, you should get 31.83 ohms. So in this case, if you compare the two, XL is greater than what? XC. So when XL is greater than XC, we are going to look for the condition, the three conditions we stated before, the equation that suits it. So that means our XL will be at the front. We will now deduct what? That means we are going to deduct our XC from XL. So when you find the difference between XL and XC, it's going to give you what? 5.87. That is 37.70 minus 31.83. It's going to give us 5.87 ohms. So we pick our formula. If you go back to the first case, I said when XL is greater than XC, our Z will be what? R squared plus XL minus XC squared. So, and we know that our XL minus XC from what we just did is what? 5.87. So, and our R is what? 5. So we are going to square both of them and add them together. So when you do that, you get 7.71 ohms. 7.71 ohms. So, and from previous class, we know that I is equal to V over Z. I is V over Z. What is our V from the question? Our V is 300. And what is our Z? We just calculated the Z as 7.71 ohms. So we should divide 300 by 7.71. It's going to give you what? 38.91 amps. 38.91 amps. Then if you look at the second question, say we should find what? The phase difference between the supply voltage and the current. So we are looking for phi, and from the previous slide that we just did a few minutes ago, we said that our phase angle is tan phi. We said tan phi is equal to XL minus XC divided by R. So to find phi, we are going to find the arctan of XL minus XC divided by R. So what's our XL minus XC? We calculated as 5.87, and what's our R? 5. So when you find the arctan of this expression, it's going to give you what? 49.58. So that is that about that. Let's go back a bit. So our C says the voltage across the coil. The voltage across the coil. And what is the coil? As we said, the coil is the combination of R and L. R and L. So from the previous class, you know that if you want to find the voltage across that, we have to know the current, and we have to know the Z. of that coil. So you know that you can find that because we can square R plus XL squared. Is to find the Z of the coil is R squared plus XL squared. You have to refer to the last class we did for you to remember this. So we put the value of R, we put the value of XL. So 5 squared plus 37.70 squared, that will give us 38.03. so the voltage across the coil, we have been able to determine the current. And what did we get for the current across the coil? The current across the coil, we got a particular value for it. So we are going to multiply that I times Z. So it will be 38.91 times 38.03. So if you multiply that, you are going to get 1480 volts. So the phase angle of the coil would now be equal to arctan XL over R. This formula is also from the last class. So if you find the tan, arctan is going to give you 82.45 lagging. This is coil. I told you about it is coil, and this is lagging. So I think we have also talked about how to DC is what DC is we should find the voltage across the capacitor. The voltage across the capacitor, we know the current as 38.91 and we have our XC. So our VC will be equal to what? IXC. So if you input the values, you are going to get what? 1239 volts. So this is the phasor diagram. You should be able to draw the phasor diagram because we have done the basics of phasor diagram. So you should find time and study this phasor diagram so that you'll be able to reproduce it if you are asked to do so in the test or in the exam. So we also have a case where you have series connected impedances. So for series connected impedances, the total circuit impedance can be represented as a single LCR circuit or RLC circuit, as the case may be. So by combining all the values of the resistance together, you take the resistance, you put them together, you take the capacitance, you put them together, take the inductance, you put them together. But you must remember that when you are finding the equivalent of the capacitance, you have when you connect them in series, it's 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3 to 1 over CT. So please remember that from basic physics. So this is an example of what we are talking about. If you look at this, we have a coil. This is a coil, this is a coil, and this is another impedance. So we have three impedances: impedance 1, impedance 2, impedance 3. So each impedance consists of what? Two elements. So what we are going to do now is to add R1 plus R2 plus R3, and that's what you have your R1, R2, R3, and you have two L's, L1 and L2. You add them together, and this L1 and L2, and we have only one C. You put it there as C. You combine them together to form an equivalent circuit like this. So this is an example of what we are talking about. So the following three impedances are connected in series across a 40 volt 20 kilohertz supply. 1, a resistance of 8. 2, a coil of inductance 130 microhenry and 5 ohms resistance. And 3, a 10 ohm resistor, sorry, there should be ohm here, a 10 ohm resistor in series with a 0.25 microfarad capacitor. You now say calculate the circuit current. You want to look for the current, the circuit phase angle. We want to look for the phase angle and the voltage across each impedance. So let's proceed. This is the equivalent diagram. I will go through the circuit diagram and call the questions again. He said the question said the following three impedances are connected in series to a 40 volt 20 kilohertz supply. So if you look at it, this is 40 volt and this 20 kilohertz supply. So this is the supply across these elements, across these three elements. So the first element is a resistance of 8 ohms. This is it, a resistance of 8 ohms. So the Z1 is what? 8 ohms. Then they said a coil of inductance 130 microhenry, 130 microhenry and 5 ohm resistance. This 5 ohm resistance and 130 microhenry. This is the combination of these two forms our Z2. And the last one says that a 10 ohm resistor in series with 0.25 microfarad capacitor. This is 0.25 microfarad capacitor, and this is 10 ohm resistor. So what do? We have to add the resistances. So that is 8 plus 5 plus 10. 8 plus 5 is 13. 13 plus 10 is 23. So this is 23. So if you look at it, we have only one of these, one of the inductor. So this is 130 microhenry, and we have only one of the capacitor, which is 0.25 microfarad. So you have this equivalent diagram. So now what do we want to do? We are told to find what? A is to find the circuit current. We want to find this I, which is the circuit current. How do we find the I? You know that I is what? V is equal to IZ. You know V is equal to IZ. So I will be what? V over Z. So we know our V, which is 40. We have to find our Z, and our Z must be what? The combination of these three. It must be the combination of these three. So the first thing we do is that we find the impedance across this inductor, and we also have to find the impedance across this capacitance. That is, you have to look for the inductive reactance. You look for the inductive reactance, look for the capacitive reactance. So we compare the two to know which formula we are going to use. So if you look at it, you are looking for the inductive reactance, which is XL, which is 2 pi FL. So if you put the values inside, you are going to get 16.34 ohms. 16.34 ohms. If you look at the capacitive reactance, when we want to find it, XC is equal to what? 1 over 2 pi FC, which is equal to 31.83 ohms. If you calculate it from here, if you compare these two, you see that our XC is greater than what? XL. So we are going to subtract what? XL from XC. So that's what we have here, XC minus XL. And when you find the difference between these two values, you have 15.49 ohms. 15.49 ohms. So you are going to square the R and square the difference between XC and XL, and we are find the square root. So, and that's what we did there. The circuit impedance Z will now be equal to what? R squared plus what? XC minus XL squared. So which is equal to root of 23 squared plus 15.49 squared. When you do that, you should get 27.73 ohms. So the circuit current I is equal to V over Z, as I told you earlier. So, and our V is 40 and our Z is 27.73. So if you divide it, you are going to get 1.442 amps. 1.442 amps. So the question B is saying that what? We should calculate the phase angle. The phase angle, and we know for this case our phase angle is phi is equal to arctan of what? XC minus XL over R. XC minus XL over R. So what do we have? If you do it, our XC minus XL is 15.49, our R is 23. So if you look at it, it's 33.96. Leading. Why is it leading? Because the value of the capacitance is more than that of the what? Inductance. So we are going to have leading. So C says we should find the voltage drop across each impedance. voltage drop across each impedance. Since we know the current across the current flowing in the circuit, the same current will flow through each of the impedances Z1, Z2 and Z3. So by our formula we know that V is equal to IR for the first impedance, because for the first impedance the only thing we have is resistance. So it will be what? It will be 1.442 times 8. 1.442 times 8. So for the second impedance has 5 ohm resistor and 130 microhenry. Then what did we get for the Z of that one? Let's go back. If you look at the Z of that one, we got what? I think we've got 16 points. We got, no, what did we get? No, not here. Let's see. Okay, we got 17. Yeah, we got for the XL. If we are going to find the Z, we are going to the Z for this one here. The Z for this one will be what? 5 squared plus the inductive reactance that we got, and the inductive reactance is what? 16.34. So, and that's why you have 16.34 here, 16.34. So you square it and you find the square root. So when you do that, you get 17.09. Then you multiply it by the current, you get 24.64. The same thing we do for this. You know, we have the Z3 is what? Is a 10 ohm resistance in series with 0.25 microfarad, and the capacitive reactance of the 0.25 microfarad is 31.83 squared. We have calculated that before. So when you multiply it by the current in the circuit, you get 48.11. So the 40 volt supply is the phasor sum of V1, V2 and V3. So we move to series resonance. Series resonance. There are some examples in the textbook we are using, so you should consult them so that you know how to do all these things. You should be able to find the phasor sum of the voltages. You should be able to draw it too. You should be able to draw it. So please consult the textbook. So the series resonance, as stated earlier, for an RLC series circuit, when XL is equal to XC, the applied voltage V and the current I are in phase. This effect is called series resonance. It's called series resonance. And when series resonance occurs, there are about 6 things that must take place that happens. You should take note of these 6 things. The first thing is that VL is equal to VC. You should take note of that. VL is equal to VC. Then our Z is equal to R. Z is equal to R. This means that the minimum circuit impedance possible in an RLC circuit. So that about that. And you should know that our high is equal to what? V over R. Our high is equal to V over R. Then since XL is equal to XC, then 2 pi FRL is equal to what? 1 over 2 pi FRC. Please take note of that. From which FR squared, if you find FR squared, because when you cross multiply and you are looking for FR, so FR squared is what? 1 over 2 pi square LC. So when you do your calculation, you find the square root and all those things, you should get FR is equal to 1 over 2 pi into square root of LC. So this is at resonance. So this is what happens at resonance, the frequency at resonance. Then the series resonance circuit is often described as an acceptor circuit since it has its maximum impedance and thus maximum current at resonant frequency. Also, typical graph of current and impedance against frequency are shown in this figure. So you should take note of this figure. It is very important figure when you are designing resonance circuits. So we have a worked example on that too. A coil of a resistance of 10 ohms and an inductance of 125 millihenry is connected in series with a 60 microfarad capacitor across a 120 volt supply. At what frequency does resonance occur? At what frequency does resonance occur? And find the current flowing at resonance frequency. Find the current flowing at resonance frequency. So if you remember, we are supposed to, the first thing is that we should find the current flowing. Okay, we should find the resonance frequency. So to find the resonance frequency, we know that our FR is what? Is 1 over 2 pi root LC. 1 over 2 pi root LC. And what is our L? From the question, what's our L from the question? Let's go back. Our L is what? 125 what? Millihenry. So this is it, 125 millihenry. And the other one is what? 60 microfarad. So this is 60 microfarad. So you don't need to, when you are doing your calculation, you don't need to do it the way they are doing it. You can press your own calculator and put the values, but they want to try to use indices. That's why you are seeing this one like this. You can write your, let me see, you can see your, this one is what? 0, you can see is 125 times 10 raised to power what? Minus 3. So don't confuse yourself. This one you can see is 60 what? 60 times 10 raised to power what? Minus 6. And you press your calculator. So if you press your calculator and you do all this calculation, you should get this answer, 58.12 hertz. So the frequency is 58.12 hertz. So and we know that at resonance, XL is what? Is equal to XC at resonance. XL is equal to XC, and the impedance, as we said, Z is equal to R. Z is equal to R. So the current will now be equal to what? V is equal to I is equal to V over R. If you remember, that's what we stated here, that our I is what? V over R. So that is the same formula we are going to use to find the current. So what is the value of our V? If you go to our question, you discover that our V is what? 120 what? 120 volt. 120 volt. And our R, what is our R from the question? Our R is what? 10 ohms. So if you divide 120 by 10, we are going to have 12 amps. 12 amps. So that's that about that. So we move to the next slide. The Q factor. The Q factor. So at resonance, if R is small compared to XL and XC, it is possible for VL and VC to have voltages many times greater than the supply voltage. So that can occur. So when that occurs, we have voltage magnification at resonance. We have voltage magnification at resonance, and so it is given by the voltage across L or C divided by voltage supply. So the supply voltage. So this ratio is a measure of the quality of a circuit as a resonator or tuning device. This is usually used in radio transmission, and this term, the ratio of the measure of the quality of a circuit, is called the Q factor. Q factor. So the Q factor is VL over V. That is the voltage across the inductor over the supply voltage V. And we know that VL is equal to IXL, and our V is equal to IR. So when you divide it, because it is in series, the current cancels out. It will be XL over R. And we know our XL to be what? 2 pi FRL at resonance. Instead of putting F, it will be FR. So that is how we get this. So alternately, if the circuit consists of a capacitor, it will be VC over what? Over V. and IXC over IR. So it will be now XC over R. So and what's XC? XC is equal to 1 over 2 pi FRC. So if you put it here, you are going to get this. So at resonance, we know that at resonance, FR is what? 1 over 2 pi root of LC. We just did that a few minutes ago. So we can find, you can see 2 pi FR is equal to 1 over root LC. So the Q factor is equal to what? 2 pi FR over L, 2 pi FRL over R is equal to 1 over root LC multiplied by L over R. So what do we have? We now have 1 over R into square root of L over C. So this is the expression. This is the expression. So or you use this. Depends. You can use this. So those are the ones you can use. So let's go and see an example of that. So we say a series circuit comprised of a coil of 2 ohms, an inductance 60 millihenry, and a 30 microfarad capacitor. Determine the Q factor of the circuit at resonance. So we know that at resonance, what happens at resonance? Let's go back to the question. What were we given? Let's write them out. We are given what? We are given C. You have C. What are we given again? We have R. This is our R in ohms. Sorry, it should be in ohms. We have our L. So this is our C and this is our L. So we have that 3. So we have to go back and see which formula combines R, L and C from the formulas we have for the Q factor. So if you go back, if you look at this formula, this is the formula that combines the 3 together. So this is the formula that combines the 3. So it's this formula that we are going to use, 1 over R square root of L over C. So it should be 1 over R square root of what? L over C. So if you look at it, so this is the formula, this is it. Then we substitute. Our R is 2, so it's there. Our L is what? 60 times 10 raised to what? Power minus 3. And our C is what? 30 times 10 raised to power minus 6. So if you do the multiplication and you find the square root and multiply by half, you are going to get this. Note that it does not have any what? Does not have any unit. Does not have any unit. So that is that about that. I think that's where we are going to stop for this class. So in the next class, we are going to see how we can apply this to bandwidth. You can see how we can apply it to bandwidth, and after that, we are going to also look at power in AC circuits. Power in AC circuits. So you should go back to the textbook and make sure you solve questions. Make sure you solve questions, because that's the only way you can learn. So thank you very much for listening.